Hello, everyone. I'm going to talk about our work on outlier detection in a union of subspaces. This is a joint work with Daniel Robinson and René Vidal. In recent years, we have witnessed a large amount of available data in computer vision. Big data has created great opportunities for finding new information from data. However, the challenge is that most of the collected data in these days are unlabeled and weakly labeled, and therefore we need algorithms that can find patterns in this data. In the past decade, Subspace Classroom, as the previous speaker has talked about, has emerged as a powerful tool for learning multiple groups from unlabeled data. It works under the assumption that the high-dimensional visual data often lie in low-dimensional subspaces. In face classroom, for example, images of the same face under varying illumination conditions lie approximately in a low-dimensional subspace. While subspace classing methods can cluster data into their respective subspaces or groups, their performance can be sensitive to outliers, which are points that do not lie in the union of subspaces. And the goal of this work is to address outliers in a union of subspaces. Our outlier detection method is based on the idea of data self-representation. Concretely, given a dataset denoted as X, the first step of our algorithm is to solve the optimization problem shown on the top. It finds a coefficient vector Cj for representing a data point Xj, using all the other data points as a dictionary. We use a synthetically generated dataset to illustrate the idea. So we take inliers to be images of a face and outliers to be other arbitrary images. A key observation of our method is that if we take xj to be an inlier and write it, and solve the optimization problem on the top, then the coefficient vector Cj is going to have the property that its non-zero entries are going to correspond to other inliers only. And on the other hand, if xj is an outlier, then the non-zero entries of Cj are going to correspond to both inliers and outliers. Motivated by this observation, we are going to use a graph to capture the difference behavior in the representation vector of inliers and outliers. And in particular, in this random walk graph, there will be no transitions from inliers to outliers. And therefore, a key observation in our algorithm is that any random walker initialized on this graph will always end up in the set of inliers. Therefore, we further compute the stationary distribution of this random walk. And in this stationary distribution, the outliers will have low or zero probability, while inliers will have higher probabilities. And we have shown that this stationary distribution can correctly identify outliers by thresholding the probabilities. As experiment, we have tested our method on the extended EOB face, as shown in this slide, as well as two other databases. And we have compared our method with a wide range of other robust PCA-based outlier detection methods. And our method is illustrated in red. In our experiments, we have shown that our method achieves the best outlier detection performance on these three databases. In conclusion, in computer vision, we have a large amount of unlabeled data which are often corrupted by outliers. And in this work, we have designed an algorithm to reject those outliers in a union of subspaces. Thank you for your attention.